filled with beautiful objects, from shining stars to amazing clusters of galaxies, to clouds of gas and dust. And one force has created them all: gravity. This month, we're looking at how the wonderful shapes and spectacular structures we see in the universe have been created.
Welcome to the Sky at Night. Spring is finally here and the nights are warmer, at least in theory, and we've escaped the bright lights of the city to come and join this rowdy bunch of amateur astronomers at the Brecon Beacons Astro Camp.
Keen astronomers have come from hundreds of miles away, and they're setting up camp in the hope of using the coming darkness to see deep into the night sky.
See some texture. Of course, being Britain, the weather isn't on our side, and it's pretty cloudy. But we're hoping there'll be some breaks in the clouds later on. Whatever the weather, we're going to use the time to explore the extraordinary ways in which gravity shapes the objects in the night sky.
Coming up, I'll be finding out how gravity makes stars and planets round, and why despite the power of this force, they're often not as round as they seem.
Chris North and John Colshaw are here, and they'll be taking us on an intergalactic tour to show us how gravity sculpts each and every galaxy.
And we'll be seeing gravity in action right now, as it creates an extraordinary drama in Saturn's rings.
This is the first time that we've ever seen anything like this.
Plus, Pete Lawrence and some campers will be showing us simple tricks to capture star trails.
Oh, that's amazing!
As darkness sets in, we're still waiting for the clouds to properly break. But some bright stars and planets like Mars are shining through. So while we wait and hope, here's Paul Abel with a guide to what it's possible to see if we embrace the dark and if the skies are clear.
Well, here we are in Wales in a lovely dark site, and viewing the night sky from a place like this is really very different from viewing it from a town centre. The main reason for that is, of course, there's very little light pollution here, but another significant reason is that our eyes can become very dark adapted in sites like this. And the reason we have dark adaptation is because our eyes manufacture a chemical called rhodopsin, which allows us to see in the dark. Unfortunately, that chemical is completely destroyed by bright white light. You can experience all of this for yourself. The first thing you'll notice when you step out into a dark sky are the bright objects in the sky, like the moon or the planets, Mars and Jupiter, we have around at the moment. Later on, you'll notice the bright stars, like Arcturus shining away up there. After 10 or 15 minutes, you'll notice the fainter stars that make out the main constellations, like the faint stars that mark out the handle of the plough. After 25-30 minutes, you become totally dark adapted, and in a dark site like this, the sky is literally ablaze with stars. But perhaps the most impressive thing is the sight of the Milky Way running down through the constellations. You can use exactly the same process for getting the most out of your telescope, because the more you look, the better you'll be able to see. If we take Saturn, for example, initially the view is not too impressive. We notice it's a planet surrounded by a ring system, but after 5 minutes, the subtleties of Saturn start to come out. We notice the delicate cloud bands, the pastel hues, the brighter zones, and the rings themselves take on more of a 3D effect. So the moral of the story is, in order to get the best views out of your telescope, spend as much time as you can looking.
Frustratingly, we are still not getting any decent holes in the clouds. So let's take a look at the awesome creative power of gravity.
Now, whatever you look at in the night sky, whether it's a star or a planet, you're looking at an object that's basically a sphere.
The sphere is the most common shape in the universe, but when it comes to the cosmos, a sphere isn't always what it seems. Perfect spheres are actually surprisingly rare in space. To understand how gravity forms spheres, and why they're often not perfect, you have to start with how objects like stars and planets form out of stardust. It's gravity that caused the planets to form in the first place, but gravity is also the key to their spherical shape. Let's imagine that these sugar cubes are lumps of rock in the early solar system, orbiting a young sun some 4.6 billion years ago. Gravity pulls them towards each other, but gravity has no preferred direction, so they come in from here, from here, from here, from all over. The shape you end up with is the only shape that looks the same from every direction: a sphere. Gravity created the blue planet we call home. But although it may look flawless, our planet is not perfect. Imagine I start at the equator and I walk all the way round the Earth. By the time I get back to the beginning, I would have walked 40,000 kilometres. Now let's say I do the same thing, but this time pole to pole. By the time I get back to the beginning, I would have actually walked around 130 kilometres less. That's because the Earth isn't a perfect sphere. It's actually a bit fatter in the middle. And it's not just Earth. Most of the planets in our solar system also have a bulge around the equator. The reason some planets grow a bit fatter around the middle is because of the way they rotate on their axes. It's because of a phenomenon we can experience here on Earth. Spinning something causes it to be thrown outwards, away from the centre. These chains are the only things keeping me and this chair from flying off into the distance. The same thing happens to a planet when it spins. Gravity acts like the chains, pulling everything inwards, but the speed of rotation pushes everything outwards. Just like the chairs on this ride, as a planet rotates on its axis, it grows wider around the middle. And of course, the faster we go, the greater the effect. In our solar system, Jupiter spins the fastest, taking just 10 hours to complete one rotation, and therefore it has an enormous bulge. Its circumference is 29,000 kilometers greater when measured around the equator rather than the poles. Venus spins the slowest. A day on Venus is 243 Earth days. As a result, Venus has no bulge at all and is close to a perfect sphere. In general, the faster the spin, the bigger the bulge. But there is one rather big exception to the rule that we still don't fully understand. Our Sun is very large, and it rotates at nearly 7,000 kilometers per hour. That's incredibly fast, so you'd expect it to have a bulge, but it doesn't. It's an almost perfect sphere. This astonishing discovery was only made in 2012 as a result of the most detailed measurements of the Sun that have ever been taken. Dr. Chris Scott is a solar expert and a space scientist. He's been trying to understand this intriguing mystery on our astronomical doorstep. So why did it take so long to get this measurement?
It's a really difficult measurement to make, as it turns out. When you get up into space, you can see the Sun and the Sun's atmosphere, and it's not smooth. There are eruptions of material off the surface of the Sun all of the time. The new spacecraft that's enabled these measurements is called the Solar Dynamics Observatory. It's a solar telescope that's in orbit around the Earth. So it's sending back something like 15,000 images a day. These images it's taking are 10 times HD resolution. They'll actually be able to work out that the Sun is much, much rounder than it has any right to be.
So what do you think is causing this result?
Well, it's another force of some sort that's got to be stopping it from bulging. So the theories have been perhaps that the poles would be slightly hotter, and so maybe it would expand out a little bit more, and so that would even up the difference.
But it seems unlikely that it's just the right temperature to sort of make it very spherical.
Indeed, and there's no evidence that there is this temperature difference. It could be a magnetic field. So we know that the sun has a strong magnetic field. It comes out of the sun at north and south poles. Could there be some concentration of magnetic field that's stopping the material, like an electromagnet on the fairground ride, pulling the cars in? Is there some force that's stopping the material from bulging out? And again, there doesn't seem to be much evidence that there's that strong a force. So perhaps it's something in the solar interior. Perhaps some part of the solar interior isn't rotating as fast as we thought it was, or perhaps there's some kind of stresses going on between the different layers to distribute the mass of the sun in a different way from how we thought.
In a previous program, we actually looked at sounds travelling through the sun. Do we need something like that to try and solve this mystery?
Yes, and it's a really cunning technique called helioseismology,
yes.
and it's looking at the interior of the sun by using these shock waves from the explosions in the sun's atmosphere. And just like we can use earthquakes on Earth to study the interior of the Earth, you can do the same thing on the sun by looking to see how long it takes the shock waves to propagate through, and that tells you something about the solar interior. We've used this technique for some time now, and we're clearly the answer's in there somewhere, but we didn't know to look before. Now we know to look.
Thanks very much, Chris. So we'll have to wait to resolve this particular mystery. Although gravity is the master sculptor, shaping the planets and the stars, there are other factors at work, some of which we don't yet fully understand. But what fascinates me is that something as simple as an object's shape can reveal so much about it. Back at Astrocamp, we can just see some stars poking through the odd holes in the clouds. If it were a little clearer, we could train our telescopes with some objects shaped in different ways by gravity. There are two very special objects to see in our night skies this month. The dwarf planet Ceres and the minor planet Vesta. These two unsung heroes of our solar system lie between Mars and Jupiter. But what makes them fascinating is their relative sizes, which means they sit either side of a very significant divide. At about 1,000 kilometers across, Ceres has enough mass for gravity to have carved it into a smooth sphere. That makes it what is known as a dwarf planet. But that's not the case for Vesta. Because it is smaller, its gravity is too weak to form a sphere, leaving it with a more irregular shape. It fits into a lesser category, a minor planet. To become a major planet, like Earth or Jupiter, a body needs to be spherical, which rules out Vesta. But it also needs to have cleared out all the material in its orbit, which is where Ceres is wanting. The orbits of both Ceres and Vesta lie deep within the main asteroid belt, but the planets themselves aren't big enough for their gravitational fields to have cleared out the nearby asteroids, which is why they're not major planets. But they're still great to see.
Coming up, Pete's guide to the highlights of what to view in this month's night sky. We can't see much at the minute, but here's Pete with some tips on how to take dramatic astronomical photographs when the clouds clear.
It's really easy to take some fabulous photographs of the night sky using nothing more than just a camera and a tripod. Now this month I'm going to show you two different techniques which can be used to take some really great shots. First up, a wide shot of the sky that captures a panorama of the stars. Now the best type of camera to use is a digital SLR camera. Now you need to fit a fairly wide angle lens, say 50mm or shorter focal length. The camera needs to be set into a manual mode, and you need to focus that lens as accurately as possible. You must use a tripod to keep the camera steady, otherwise the stars will appear blurred. Now to get the best results, it's useful to have the aperture or the opening on the lens as wide as possible, because that allows all that delicate starlight to come into it. So use the lowest f number you can on your camera. You want a fairly high ISO, say between 400 and 1600, and experiment with an exposure time of around 30 seconds. Sadly, the clouds are stopping us imaging tonight, but you should end up with a photograph like this. Now when you start taking longer exposures of the night sky, if you look at each individual star carefully, you'll see they are no longer pinpricks of light, but they start to elongate into little lines. Now we can use that effect creatively to take star trail photos, and that's our second type of astrophotography. A star trail is a long exposure photograph that captures the apparent motion of the stars as the Earth rotates. The trick here is to do the opposite to the wide shot method. To get those lovely long streaks of brilliant light, you need a long exposure time. 15 minutes will do, but you can easily push it to 30 if you're confident of clear skies. Remarkably, some of the campers managed to get some images last night during a momentary break in the weather. Yeah, oh, that's amazing. So you've got the lovely green lasers pointing up there. And look at that star field behind there.
It was just a gap in the clouds and everybody got so excited. It was just trying to capture the excitement of the astronomers as well as the star field, so it was like combining the two.
And did somebody hold a red light there?
No, I kind of like annoyed everybody flashing my red light. I just said, I've just got to do it for a couple of seconds. So a bit of like red light painting.
So you
just
painted
to bring
everybody, in red light. But that is really effective, and it contrasts beautifully with the green of the laser. Really effective. That's come out so well. We've got Cassiopeia down there, the W, And it's great, you've got a bit of horizon in there as well.
I think it just adds to that, otherwise it just sort of loses itself, so it's nice to have a tree or, like in this case, camper van and a few tents and things in there.
Brilliant result.
Thank you.
Now while you're taking your long exposures, why not take that time to explore the night sky in a bit more detail? So here are my highlights for this month. Galaxies are plentiful in May. Below Mars at the moment is a distinctive star shape known as the Sail, part of the constellation of Corvus. Two stars in Corvus point to M104, the famous Sombrero Galaxy. A small telescope shows its distinctive shape well. The plough or saucepan sits roughly overhead around midnight. Close by the star marking the end of the saucepan's handle, you'll find the wonderful Whirlpool Galaxy M51. Visible in good binoculars, a telescope is required to bring out its spiral shape. Early in the morning of May the 24th, a short but intense meteor shower may appear to come from the constellation of Camelopardalis. If it arrives, the meteors will be due to Earth passing through the debris of comet 209P Linear. Finally, Saturn reaches opposition on May the 10th, making it bright in the sky. Look for it due south around 1 AM. Through a telescope at opposition, the rings can appear to brighten quite noticeably.
With the clouds set in for the night, we've retreated inside to look at this month's Astro News. We have to start with the death of Laddie, the NASA spacecraft that crashed into the moon this month after completing its mission to look at the moon's atmosphere, or at least the dust that's kicked up from the lunar surface. And it set back just before it died this amazing sequence of pictures. So you see the lunar horizon there, and as we flick on, what you see is a rather magnificent lunar sunrise, something we haven't really seen like this since Apollo 17. It's fabulous, it's great to see it, and actually if you go back a few minutes, what you can see here is that glow is dust in the solar system, what we call the zodiacal light, but seen from the surface of the moon. It's a beautiful thing.
It is, illuminated by the sun. Fantastic. Our next story comes from the Kepler mission, whose mission in life has been to go out and find exoplanets, and it's done a fantastic job so far. But of course, the holy grail is to find an Earth-like planet, and it looks as if it's done just that. And this is an artist's impression of an exoplanet called Kepler 186f, and it's going around a red dwarf, which is sort of slightly colder than our sun. But we've found this on the outskirts of the Goldilocks zone, so it's an Earth-like planet which could have life. It's slightly bigger than Earth, but it's just what we've been looking for.
Now, we've also made another discovery just in our own neighbourhood. This is the earliest impression of a star that's been found just 7 light years away. So that makes it the 4th closest star known. We only found it in the last month or so. The reason we've only just found it is that it's rather cool. In fact, so cool that it has a temperature that you'd expect at the Arctic, minus 13 degrees centigrade.
To me, that's counterintuitive. Stars shouldn't be cold.
You could think of this as a really big planet, but we'll also have weather and clouds just like the giant planets do.
The definition, planet, star, where do we lie? It gets much more interesting.
Yeah, we've never really decided, so let's just say we found a new object, and it's very exciting.
Now back to how gravity shapes the night sky. Chris North and John Corshaw are looking at how gravity works on a huge scale to create galaxies of many different shapes. With most of the campers on their way to bed and the clouds still thick, Chris and John are having to resort to some well-chosen photographs to guide us around an extraordinary spot in the night sky.
Well, one particular zone we've been looking out for tonight, just above the constellation of Virgo, is an area where many a time you wouldn't see too much detail in there, but get to a dark sky area like the Brecon Beacons and place a scope on this particular zone, and it comes alive wonderfully, and you can see exactly why this area is called the realm of the galaxies.
There are dozens, if not hundreds, of galaxies to look at with a small telescope in this area of the sky, and a bigger telescope will obviously show you more in something that's called the Virgo cluster. This image here shows us half a dozen bright galaxies, but then dozens more fainter ones, all different shapes and sizes. You can see elliptical galaxies that look like spheres, so we've got a close-up of a galaxy here, and it looks like a round spherical blob. There's not a lot of structure there.
Yes, rather like a supermassive star.
That's the combined light of billions of stars all glowing together. So it's quite a humbling thought when you think of that.
So if we take a look at the very familiar spiral galaxy, what would be the forces that would cause a galaxy to form rather like this?
This is one of the galaxies in the Virgo cluster. This is M100, Messier 100. And you can really see the characteristic spiral form. And what this doesn't really tell is quite how flat this structure is.
And that's very much the way that gravity evolves our own solar system around the sun, isn't it? This familiar flat disk.
Both the solar system and galaxies form from roughly spherical-ish blobs, groups, clumps of gas and dust, and they collapse under gravity. Now, if there's a preferred direction of rotation to that gas and dust, then that will settle into a disk, and that's what happens with spiral galaxies like this. The gas and the dust collects into this disk, and then new stars form, and we see the patterns we see today. And then in the solar system as well, the gas and the dust collects into a disk, and it's out of that gas and dust that the planets form, and that's why they're all in a same plane. Essentially the same process, just because of this common axis of rotation.
What's behind the formation of the elliptical galaxies?
Well, this is an example of an elliptical galaxy. What's happened is that elliptical galaxies have formed from the mergers, called the combinations, the collisions between other galaxies over billions of years. And because that's lots of things combining together, there's no one favoured direction, and you don't get this flat disk that we see in the spiral galaxies.
Isn't it fascinating to think that at the centre of galaxies, where the stars are much more dense and much more tightly packed, imagine being on a planet orbiting one of those stars. What kind of a night sky would you see?
There'd certainly be many, many more stars in the sky. And one of the reasons we can look at the Virgo cluster and study it in the detail we can is because we're looking out of our own Milky Way galaxy. If we're in the centre of a galaxy and there were stars all around, we wouldn't be able to do extragalactic astronomy and look at other clusters. There might be no evidence we were inside a cluster of or group of galaxies at all. So we're really in quite a special location here to be able to look out of our galaxy and see the rest of the universe.
Next, we're sticking with gravity, but this time how we can see it in action closer to home.
Now, one of the most beautiful things to look at in the night sky must be Saturn. 6th planet in the solar system, orbiting about 9 times further out from the sun than we do. And with relatively basic equipment, it's possible to get a beautiful view of its magnificent rings.
And it's to these rings that we turn next, because we've seen something that's never been seen before. A moon forming amongst the rings. And earlier today I talked to Dr. Katrina Jackman about these observations and about what they might mean for the early solar system.
The NASA spacecraft Cassini has been orbiting Saturn for the last 10 years, and in that time it sent back incredible images of the gas giant, of its moons, and of its glorious rings.
Well, Cassini sent back some of the most spectacular images of the last decade, but the one that people are excited about right now is this. So what are we looking at?
So this is a beautiful image that the Cassini spacecraft cameras have taken when the spacecraft was looking down on top of the rings, and this is an image of a very bright feature on the outer edge of the A ring.
And so we're actually looking at this blob down here in the corner.
It's a very special blob. It's actually the formation of a brand new moon. So it's material clumping together under its own self-gravity, and in doing so dragging material out of the rings with it. So a very small moon at the centre, probably less than a kilometre in diameter, but as it's orbiting around within the rings, it's dragging local ring material and collecting it onto itself.
So how unusual is this?
This is a one-off. This is the first time that we've ever seen anything like this. This is our first time we've ever seen a moon being born in real time.
Saturn already has 60 moons.
It does.
Is it continually producing more?
We don't think so, and that's actually what makes this opportunity so rare, is that, as you say, Saturn has more than 60 moons. It has some very famous icy moons in particular, like, for example, Enceladus, and it's thought that Saturn's rings used to be a lot bigger, and that moons like Enceladus were formed from the rings. And so as those moons were formed by material in the rings clumping together, they took a lot of material with them. And so the rings that we have today are quite depleted relative to what they once were.
So this was 2013, this image, so,
Yes.
so from last year. Do we know how our new moon's doing? I sort of want it to succeed.
Yeah, I want it to succeed too, but we're not sure what's happening to one part of it. It's broken in two. So Object 1 is moving in through the rings, and as of last week, it's causing a lot of disturbance locally, and it's pulling and tugging at the ring material near it. Object 2 has gone the other way, so Object 2 has migrated out of the rings, and it's actually too small to be observed directly by Cassini, but we may catch it again on a further orbit.
Well, I hope so. And of course this tells us about the rings, but it's also just telling us about physics. And if we go back 5 billion years or so to a solar system that looks something like this disk of material from which the planets are forming looks rather like a ring system.
It does, yeah. So this is a disk that formed from the solar nebula, and from this disk you had planets and protoplanets forming and then migrating outwards from the point of formation. And so observing the formation of a moon like this and then its subsequent migration out is kind of a window on what might have happened in the formation of the early solar system.
And so Cassini's been there, as we said, 10 years, and we're still getting fabulous science from it. What's next for the mission?
So Cassini's got another 3 years to go. It's going to finish in September of 2017 with a plunge through Saturn's atmosphere where the spacecraft will ultimately vaporize.
And that's just to get it out the way, right? It has to end up somewhere, and we don't want it crashing into anything.
Absolutely. Before it vaporizes, we're going to make the best use of the time we have left. And so the final phase of the mission is going to take the spacecraft just above the upper atmosphere of Saturn and between the inner edge of the D-ring. And so that's a hugely unique vantage point.
Between Saturn and the rings.
Absolutely. So you're looking outwards at the rings for the first time ever. That's going to shed light not only on Saturn's ring system, but on disks more generally, and on how rings and moons form more generally in the solar system.
And how gravity works wherever it is in the universe.
Yes.
Well, I look forward to seeing those images and to hearing you talk about the results. So thanks for now. Thanks a lot.
Last month, we launched a competition to give one viewer the chance to take control of HiRISE, the most powerful camera in Martian orbit, and choose a location for it to image.
We can announce the winner is John Green from Cambridge. He's chosen a spot in the canyon Hades Chasma that he thinks has an odd black mark.
Hopefully, the satellite will take the image in the next few months, and we'll put it on our website as soon as it reaches Earth.
Well, that's it for this programme.
There are wonderful star parties like this happening all over the country, so check out our website to find out what's happening near you.
When we come back next month, we'll be talking about the awesome power of impacts from asteroids in our solar system to the distant cosmos.
In the meantime, get outside and get looking up.
Good night.
And The Sky at Night BBC book is available now. Next tonight, our tribute to the great Alan Bennett continues here on BBC4 with Dinner at Noon.